Hello everyone, I'm Jin, an assistant professor at the School of Data Science, Chinese University of Hong Kong, Shenzhen. Today I'm very glad to share our work, CoordNet, data generation and visualization generation for time-film forums through a coordinate-based neural network. So here's today's talk's outline. So first of all, I will just talk about our motivation behind this work, and I will also overview the current two popular neural network frameworks, convolutional neural network and implicit neural representation. Next, I will talk about our details of CoordNet and the corresponding evaluations. Finally, I will talk about the future works based on the implicit neural representation. So first of all, currently we have witnessed the power of deep learning on processing diverse scientific data, scientific visualization tasks. So for example, in data generation, we can use convolutional neural network to handle temporal superposition and spatial superposition. And of course, we can also use generative model to produce rendering image on the different fields, and we can also predict ambient occlusion volume and add such information into the rendering pipeline to enhance our visualization result. However, all those works are just based on the convolution operation, and we need to have specific design to for specific task. For example, in temporal superposition and ambient occlusion prediction, we need to design encoder-decoder structure. While for the field synthesis and spatial superposition, we need to design decoder structure. Currently, we cannot use convolutional neural network to build a unified model so that we can just process all those kind of tasks without changing the architectures. On the other hand, beside this kind of convolutional neural network, we have a new learning framework which we call implicit neural representation. So unlike convolutional neural network, where we need to learn mapping from value to value, in implicit neural representation, we just decompose data into a set of coordinates and set values. So here, given a set of coordinates, we use the implicit neural representation to predict the corresponding value at this coordinate. Compared with convolutional neural network, implicit neural representation has several benefits. The first one is resolution independence. So we know that convolutional neural network requires to build the neighborhood connection. So here, the input data size is limited by its memory. While for the implicit neural representation, it can just handle that extremely large resolutions without any trouble, because we can just decompose the coordinate into multiple batches. And the second one is that it can just handle continuous signals. Instead of only sample at the center of this coordinate, we can also sample arbitrary places of the coordinate space. And the third one is that it's just a unified framework to help us handle diverse tasks. In computer vision and computer graphics, researchers will just use this kind of implicit neural representation framework to process image reconstruction, mesh reconstruction, and field synthesis tasks. So next one, I will talk about the details of our proposed solution. So coordinate is just a coordinate-based neural network. Given a set of data, we just decompose them into a set of coordinates such as x, y, z, and t, and we just feed this kind of information into our neural network, and then we just predict the values, and then we just compute the loss to update parameters in the coordinate. So in the mentioned four tasks, we can just decompose them into a set of coordinates like spatial and temporal superposition. The coordinate just x, y, z, t, and the corresponding output just factor. And for field synthesis, given the image location x, y, and the rendering field parameter theta and phi, we need to predict the RGB value. And for the ambient occlusion prediction, given the x, y, z, t, we need to predict the ambient occlusion value. So here, next one is that we just show the architectural overview of our approach. It just follows an encoder-decoder structure. Give a set of coordinates. We just use multiple layers as an encoder to encode the low-dimensional coordinates into a high-dimensional vector, and then we just follow one linear layer as a decoder to decode the high-dimensional vector into the corresponding value. And here we just talk about how could we apply this simple but powerful architecture into different scientific visualization tasks. So one example is about the spatial superposition. So given a high resolution volume, we just subsample them into a set of low resolution volumes. And then we just decompose the low resolution volume into a set of coordinates x, y, z, t, and feed into the coordinate to predict the corresponding value. and the low resolution volume is just sparsely sampled from the high resolution volumes. So during inference, we can just go through all the coordinates from the 0, 0, 0 to the xy minus 1, y minus 1, z minus 1 to get all the values at this coordinate, and then we merge these values to get the final super resolution volume. So here is just a comparison between our approach and other approaches. So here we highlight the difference using the yellow arrows. Based on this kind of highlight, we can see that our approach can just produce better visual result and final details compared with the rest of the approaches. So here is just a video that shows a frame-to-frame comparison using the isosurface rendering result. And here we can see that compared with the learning-based approach, our approach just can produce final result. And compared with the bicubic interpretation, our approach can just guarantee the temporal coherence. So compared with the convolution-based neural network, our approach still have one benefit, which is that it can just allow us to do the spatial super resolution unsupervisedly. So which means that even without any ground truth to train, we can still use our approach to upscale the data. So here just a comparison with the bicubic interpretation. So here we can see, as we had using the red arrow, our approach can just preserve more details and more smoother result compared with bicubic interpretation for the unsupervised super resolution. And here are just some quantitative results in terms of the PSNR, a data level matrix, LPIPS, a rendering image level matrix, and the transfer distance, isosurface-based matrix. And here we compare our approach again for data sets, and for most of cases, our approach can just achieve the best result compared with the rest of the method. And similarly to the spatial super resolution, our approach can also work for the temporal super resolution unsupervisedly. So for example, on the left, we have 100 time steps, and we can sparsely sample like 30% of the data to train our coordinate. And after training, we can just produce 600 time steps unsupervisedly. And here, this animation shows that we just generate more than 6 time steps between the two neighborhood ones in the original dataset. And here we can see that even with this kind of generation, our approach can still guarantee the temporal coherence in this transformation among different time steps. And for the ambient occlusion prediction, we just give the volume and the transfer function, we produce the opacity volume. Then we just use Monte Carlo simulation to produce the local ambient occlusion volumes, and use this data as our training samples to train our coordinate. And in the inference, we can just sample different coordinates like x, y, z, and t to get the corresponding missing ambient occlusion volumes. So here just a comparison, which also shows the difference image as the top left corner. So based on this result, we can see that our approach can just produce few errors compared with the local ambient occlusion and the other two deep learning approaches. So here are just some quantitative comparison in terms of the PSR and LPIPS. Again, our approach can just produce high values for PSR and low values for the LPIPS for most of cases. And here just a comparison of how our approach can apply to the field synthesis task compared with the existing approaches. So here we can see that in terms of the smooth transition between different fields, our approach can just preserve better compared with the rest of the method. And of course, in terms of the shape and lighting, our approach can also produce a high quality result. And finally, I would like to talk about the limitations of our framework. First of all, our approach cannot process tasks requiring global information. For example, like field recommendation. This is because that we just treat each pixel, each coordinate as an independent training sample. So in terms of the tasks that we need to require global information, coordinate cannot process it. So the next one is that our approach cannot help us to handle a complex certain space. So for example, for ensemble generation, once a certain space is extremely complex, for example, ensemble, and we only have limited training samples, it's very difficult to use CoordNet to process this kind of task. And here's the summary of our approach. Compared with different learning-based approach, we just compare the training time, the inference time, the supervision width, and like data type after task and model size. So here we can see that our approach can just work for the 2D and 3D without changing the architecture, and it can just handle after scale, and we can just handle diverse tasks, and we can use few parameters to achieve better performance. So finally, I will talk about the future works based on the implicit representation. So first of all, it's about the string data compression. As we know that implicit representation is just a natural compressor for compressing data. So here, we can just use this kind of architecture to help us to process string data. For each string, we have a compressor, and after we finish all strings, then we need to propose some kind of solution to merge this kind of compressors into a final one. The next one is about how to speed up training. So currently, we just treat each coordinate as a training sample. So here, maybe for one task, we have millions or even trillions training samples. How could we just reduce the speed up the training time so that we can just make this kind of framework more flexible into our real applications? It's still an open question. And thank you for your listening, and I'm ready to take any questions.